In this video, we're going to talk about profit, cost, and revenue. Just as a quick review, we know that profit is exactly the same or can be calculated by doing the revenue minus the cost functions. And so, since that is our profit function, we can get the marginal profit, which is the amount of profit earned from selling and producing or producing and selling one additional item by doing basically the subtraction of the marginal revenue, which is the derivative of the revenue function, minus the marginal cost, which is the derivative of the cost function. And remember, we can write that as MR of Q minus MC of Q. And so from this, having knowledge about the marginal revenue and the marginal cost can help us determine information about the marginal profit. All right. Our goal in this section is to determine when profit is going to be maximized, right? And so what we're going to do is we're going to look at how we can use marginal revenue and marginal cost to make that decision. And so I have a graph here. I'm zooming in on your revenue function and your cost function, right? And I have three quantities of items, right? So think of a graph, but I'm zooming in on this part of my graph here. Notice on this part of my graph, the revenue function is completely greater than the cost function, right? And I have three quantities, quantity one, quantity two, and then in general, a general quantity Q, all right, which I'm just calling Q here, which I'll elongate the stem, all right. And so I want to compare the marginal revenue and the marginal cost at each of these points here. So let's look at Q1, right? When I'm looking at the graph of revenue and cost, and I want to make a statement about marginal revenue and marginal cost, remember, these are the derivatives of the revenue and cost functions. And when we have the derivative at a point, we look at the slope of tangent lines. So if you look closely here, I sort of had tangent lines graphed here. At Q1, the tangent line, the slope of the tangent line of my revenue function, all right, I'll make this a little bigger. The tangent line for my revenue function looks like this. For my cost function, it looks sort of like this, right? The one from revenue is a little steeper, right? So at Q1, marginal revenue is greater than marginal cost, all right? Marginal revenue is greater than marginal cost. When this happens, now what I'm going to do here is I want to end up talking about profit, right? Since I have an inequality, I have two sides, right? Marginal revenue is on the left-hand side, marginal cost is on the right-hand side. I can treat this like an equality or inequality and subtract marginal cost from both sides, right? If I subtract marginal cost from both sides, my left-hand side will be marginal revenue minus marginal cost, and my right-hand side would be zero because I've subtracted marginal cost from itself. This means the subtraction of marginal revenue and marginal cost is greater than zero. Now, we just said above that marginal profit or the derivative of profit is marginal revenue minus marginal cost. This means that at this point, Q1, pi prime of Q1 is greater than zero, right? And so when the derivative of a function is greater than zero, that means positive, that means that profit is increasing. So profit at Q1. So I'm just going to use the words here, no need for notation here. So that means profit is increasing. All right. So when my marginal revenue is greater than my marginal cost, which we've already discussed this before, but our profit is increasing. And so I wanted to solidify and review that. Let's go to Q2, right? At Q2, right, our marginal cost is the slope of the tangent line at Q2, which is the slope of this tangent line. And then marginal revenue at Q2 is here. The marginal cost slope of tangent line is greater than at marginal revenue. And so we know that marginal revenue here is less than marginal cost, right? If I subtract marginal cost from both sides once again, from this inequality here, right? So I leave this less than symbol, right? But I subtract marginal cost from both sides. I get marginal revenue minus marginal cost. And on my right-hand side, I get 0. Remember that when we do marginal revenue minus marginal cost, that's the same thing as marginal profit, which we know is the derivative. So we know that the derivative at Q2 is less than 0. And when the derivative is less than 0 or negative, that means that the profit is decreasing. All right, so again, this is stuff that we've already discussed before, but this comes into play, right? Well, what happens at Q? All right, so I'm going to need a little more space here. So I'm going to cut and paste this a little bit. So at Q, this point Q, the marginal cost and the marginal revenue are equal. The slope of the tangent line at Q for the revenue function is equal to the slope of the tangent line and for the cost function. So marginal revenue equals marginal cost. I'm going to subtract marginal cost again from both sides of that now equation. That means marginal revenue minus marginal cost equals 0. And when I have that, I know that pi prime, the derivative of the profit function, is 0. So when the derivative is 0, we know that we have a critical point. All right. Now, when we have a critical point at Q, we can determine whether that is a max or a min by determining if the derivative changes from negative to positive, right? Well, this is almost like creating a number line, right? Well, I know if I did an F prime line, I put pi prime on that number line, pi prime of Q. This is Q in general. And at this value of Q, right, to the left, I had a greater than symbol. To the right, I had a less than symbol. Remember that this is the stuff about Q1. To the right of Q was Q2. Remember, at Q1, we said that profit was greater than 0, which meant that the profit function was increasing because the derivative is positive. And then at Q2, we plugged in Q2. We found that the derivative was negative, which meant the function was decreasing. And so since at Q, the derivative equals 0 and it changes from positive to negative, we know that this is a local maximum. All right. So that's one of the pieces of information that I get from there, right? All this stuff about critical points, local max and min still applies to our profit, revenue, and cost functions. And as we said before, what we want to do is basically maximize profit. And one of the ways that we want to maximize, one of the times that we can tell that we want to increase production is until we get to the quantity that maximizes our profit, right? So I want to maximize production at Q1. Before we said because profit will increase. And we also know that after Q1 in a graph like this, we hadn't achieved our maximum profit yet, right? And so until we receive the quantity that maximizes our profit, we're going to want to increase production, all right? And so what we've found here is that maximum profit occurs at the point where marginal profit equals 0, right? Pi prime marginal profit is pi prime of Q, right? This is the same point where marginal revenue equals marginal cost. All right, it's always going to occur that way. Now we need the extra information that the derivative of the profit function changes from positive to negative also at that point. That comes from our first derivative test. And so let's put this information together. That was more conceptual. Let's look at this with an actual example. It says, suppose R of Q equals 14 to Q minus 0.2Q squared, and C of Q equals 0.003Q cubed minus 3.6Q squared plus 1800Q plus 100,000. Find the quantity that maximizes profit and the maximum profit. All right, there are several ways to do this, right? You can do this by looking at the fact that marginal, well, let's just do it this way. I'm going to write my profit function, and I'm going to do my derivative, and I'm going to maximize that. Anytime I see the word maximize or minimize, right? In these examples today, we're going to use a lot of maximize, but I would go through the same process for if the word minimize was used. The only difference is we know that we have a minimum in our function when our derivative changes from negative to positive at a critical point instead of from positive to negative at a critical point, which leads to a maximum, right? So the first thing I'm going to do is I'm going to come up with my profit function. And so let's write our profit function here. Pi of Q. I'm going to have pi of Q, which is R of Q minus C of Q, right? So my R of Q is 1400 Q minus 0.2 Q squared. And my C of Q is that longer polynomial there. And there we go, right? Now I put this in parentheses. This R of Q does not need to be in parentheses here, right? So it can stay that 1400 Q minus 0.2 Q squared, right? But I did put this negative, this C of Q in parentheses because I have to subtract each of those terms, which means it changes the signs of those terms, right? So I'm going to have a minus 0.003 Q cubed. When I distribute it to the next term, that's going to be a plus 3.6 Q squared. Distributed to the next term, I'm going to have a minus 1800 Q. Distributed to the next term, I'm going to have a minus 100,000, if I'm not mistaken. Now, I have some like terms here. I'm going to write this polynomial with the highest exponent first, right? My highest exponent is 3. So I'm going to have a negative 0.003 Q cubed. I have a like term in this negative 0.2 Q squared plus 3.6 Q squared. When I add those together, I'm going to get a 3.4 Q squared. And I have like terms with the 1400 Q and the negative 1800 Q. That's going to be a minus 400 Q. And then my last term is that negative 100,000. So this is my profit function. So I put in a quantity for Q, and then that will spit out the amount of profit that my company is making, right? This is the function that I want to maximize. I want to maximize or find the maximum value, the quantity that maximizes the profit and the maximum profit, right? And so what I'm going to do is I'm going to find my critical point because we know that local max and mins and global max and mins may occur at critical points. So I'm going to find a derivative. I take the derivative, which is negative 0.009 Q squared plus 6.8 Q minus 400 minus 0. I'm not going to write the minus 0. So I found my derivative, and this is a derivative that has decimals, which is the case a lot of the times when we have things like profit and revenue and cost. And so what I'm going to do here is notice this thing, right? You can try to factor this if you're comfortable trying to factor. I'm not even comfortable trying to factor this, okay? And so I'm going to draw on my algebra experience to remember that, okay, well, I know I have to set this equal to 0 to solve for x. And the factoring was one of the methods that would allow me to do that, right? Now, since I'm not going to rely on factoring, since this is a quadratic equation, remember your quadratic equations can be written in the form ax squared plus bx plus c equals 0, right? That is how we can write quadratic equations. And one method that always works for solving quadratic equations is by using the quadratic formula. The quadratic formula says that you're going to have two solutions, two possible solutions at most. It's going to be negative b, which is this coefficient on this middle term, this linear term here, plus or minus the square root of b squared minus 4ac all over 2 times a. And so in this example, the a is negative 0.009, the b equals 6.8, and the c equals negative 400. And so my input variable here is q instead of x. So my solutions are going to look like this. Q equals negative b, which is 6.8, plus or minus the square root b squared, that'll be 6.8 squared, minus 4 times a, which is negative 0.009, times c, which is negative 400, all over 2 times a, which is that negative 0.009 once again. And this is what we're going to do. We're going to use our calculator to allow us to figure what these numbers are. And so I'm going to cut my calculator on. I actually did that before, but let's do this together, right? When I put this stuff into my calculator, I'm going to make sure that I put my entire numerator in parentheses, okay? So you need to put in a parenthesis on your entire numerator, and you're going to put a parenthesis on your entire denominator when you put this in your calculator, especially if you're going to do this all at one time. And so I'm going to open with a parenthesis, negative 6.8. I'm going to do the minus first. And I'm going to do second square root. Now, my square root doesn't open with a parenthesis, but I'm going to write it just like I see here, right? I'm going to put the parentheses there. Some of your calculator may open with a parenthesis. I'm going to open with another one, all right? 6.8 squared, not necessary, but I'm going to put that in parentheses since it's positive, minus 4 times negative 0.009. Close that parenthesis, and that's going to be times negative 400. Close that parenthesis. And if your square root open with a parenthesis, you need to close that parenthesis under that square root. For me, all I have to do is do the right arrow to get out of my square root. And since I opened with this square root, this parenthesis here, I'm going to close with that parenthesis. All right. Then I'm going to divide that by, I'm going to open with a parenthesis. All right, I'm just going to say 2 times negative 0.009 because these parentheses probably is getting confusing. All right, but there we go there. And I have that and completely emboldened or enclosed in parentheses. I'm going to press enter. And I get 691.26 if I rounded that to 2 decimal places. I also want to get the positive, the plus, right? Because we get 2 possible solutions. So the nice thing about these graphing calculators is that we can copy and paste, and then I can slide or scroll over so I can change that negative. Uh-oh, what happened? So that I can change that negative to a positive. So I'm going to go here, plus, press enter, and that's 64.29 and then 691.26 if I rounded those. And so I get my 2 solutions here. I get Q is approximately 691.26. RQ is approximately 64.29. Now, these are our critical points, and they're actually approximations, right? Of course, these are quantities of items, and so I'm going to round them to the nearest whole number. I'm going to say that that's 691, and I'm going to say that that's 64, right? These are the values that I put on my number line, right? So remember, what we want to do is we want to find our global max. And so what we're going to do here is we know that we're not going to have a quantity that's less than 0. So I'm going to start my number line at 0. I'm going to put 64 on my number line, and I'm going to put that 619 on my number line. Now, we know that this is 64 point something here, and this is 619 point something. Uh-oh, I think it's 691. Yes, 691. So I wrote that down incorrectly. And so this is, and I'm going to label my number line, that's pi prime, and I'm going to pick numbers that are between these intervals here to see if I have a local max or a local min, and the value that is largest is going to be my max, well, not largest, I'm sorry. We can see how our derivative changes signs at these points, and then we can determine whether we have a max or min. So since you guys already know how to do that, I'm going to go ahead and fill in the number line with what I have found. I have a negative here, a positive here, and a negative here, which means that my profit function, if I want to know where profit was increasing and decreasing, I could use these arrows to kind of guide me. When it's negative, it decreases. When it's positive, it increases, right? Which means that at x equals or q equals 64, we have a local minimum because the derivative changes from negative to positive. And at 691, we have a local max. All right. Now, 0 is an endpoint. It's usually not an important point. It's usually your fixed cost for your company, but you can see that this is also going to be a local max. But this point usually isn't that important here. All right. It just tells us what our fixed cost will be. All right. And so when we put these things together, this is where we are. And so we have a local max at 691. And so this is the quantity that actually maximizes quantity, right? So by selling and producing, and I guess you produce before you sell, so I should say producing and selling, but by selling and producing 691 items, the profit will be maximized. The maximum profit, which this question also asks us to find in this part right here, we find that by plugging in that actual 691 into our original profit function. So that's pi of 691, which equals, well, I got to go back to my original profit function, which is this function right here. And I plug in, let's just not put that box because I messed that up. But let's plug in the 691. Okay, this is an approximation, remember, because the max actually occurs at 691.26. But we're going to plug that into our original function, which is that negative 0.003. And I'm going to put the 691 in there. So I'm given an approximation. You're not incorrect if you plug in the 691.2607995, right? You're going to get a very similar answer. Plus 3.4 times 691 squared minus 400 times 691 minus 100,000. And we get 257,217, $257,217.29. And so that I can see this, I'm going to copy and paste, because although you can see it, I cannot see it on my screen. All right. And so the maximum profit, $257,000, $217.29. All right, and that is that example. Let's go to another example. In this example here, it says marginal revenue and marginal cost are given in the table below, right? It's going to be vitally important for you to read what you're given, right? This is marginal revenue and marginal cost, right? Marginal revenue and marginal cost. This is the derivative of your cost and your revenue function, right? Estimate the production level that maximizes profit. Here's that word again, maximizes. Maximizes means, okay, I need to find my critical point, put it on my number line, or find my critical points where my derivative equals 0. So find out where the marginal profit equals 0. And then make sure that the derivative changes from positive to negative at that point, and then you can call it a maximum, right? So when we're given a table of values that include marginal revenue and marginal cost, then what we can do here is we can come up with marginal profit, right? I'm going to do it right under my table. Marginal profit, pi prime of Q, right? It's just marginal revenue minus marginal cost, right? Which is what we talked about at the very beginning. Since profit is revenue minus cost, marginal profit, which is the derivative of profit, is marginal revenue minus marginal cost, MR minus MC, all right? And so when we go to this example, if we want to create another row in this table here, then all we have to do is subtract the marginal revenue and the marginal cost, right? So I get 38 minus 11, which is negative 13. So my marginal profit is negative 13. Negative 2, 3, 6, negative 1, negative 11, right? So these are my values of marginal profit here. And so what I'm finding here is that my derivative or my profit function is decreasing in negative. My profit's derivative, my marginal profit is negative here. Then it becomes positive. Then it becomes negative, right? And so somewhere between 200 and 300, my marginal profit becomes zero, right? So I'm going to do mid-number line. And this is my pi prime line, right? So somewhere between 200 and 300, my marginal profit becomes zero. Also between 400 and 500, my marginal profit becomes zero, right? Remember, we always put the values of Q that makes our derivative zero on our number line. And then we notate on our number line whether the derivative was positive before that. And so since we have a derivative that's with these negative values, it's negative. 3 and 6 are positive numbers. Negative 11 and negative 1 are negative numbers, right? This is the information about our profit function, which means our derivative, our regular profit function is decreasing, then increasing, and then decreasing, right? So that means that our profit reaches a local minimum here, and it reaches a local max here. Now, there's going to be a zero over here. Again, that's going to be a local max, but that point is not really important for us for maximizing our profit, okay? And so when we have another point where we have a max, that's going to usually be the important point. And so some number between 400 and 500 is going to be the quantity, right? Whenever we see production level, it represents a quantity. And so what estimate the quantity that maximizes profit or the production level that maximizes profit? I'm going to say about 480, right? Or any number between 400 and 500. All right, so if you wanted to say 450, 410, 411, 418, 495, any of those numbers work as long as it's a number between 400 and 500. Because we don't have the actual equation, we can't tell, right? We just know we do know that the derivative changes signs from being positive at 400 into being negative at 500. I just chose a number closer to 500 because negative 1 is closer to 0. That does not matter. You can pick 401, 500, 499, right? It doesn't matter. Pick a number between 400 and 500. I just said it's maybe approximately 480. All right. So that's my estimate for that example. So that's the table. All right. And then the last example we're going to do is we're going to use some information about the demand equation to help us rewrite revenue and find maximum profit. So in this example, it says the demand for tickets to an amusement park, if you can see. So the demand for tickets to an amusement park is P equals 70 minus 0.02 Q, where Q is the price and P is the quantity or number of people who attend at that price. The amusement park wishes to maximize revenue. What attendance will do this? And so when we look at examples like this, we have to remember what demand is, right? Your supply and your demand equations relate the quantity of items that people will purchase to the price that suppliers would charge, or manufacturers or whoever is producing the product would charge. All right. And so you relate the price and the quantity, right? Well, if I want to maximize revenue, right? There's that word maximize again that we're going to start seeing over and over again, right? Maximize means you got to think about your derivative, your critical points, and all of that. But if we want to maximize revenue, right? Well, when I see this, I got to think about what revenue equals. Remember, revenue equals price times quantity. Now, this is an equation, or this is our revenue function, but it has two variables. I don't know the price, right? I don't know the price. They don't tell me the price. However, they give me the price in terms of the quantity, right? And by that, they isolate P and give me an expression with only Q in it, right? But here I have my revenue. I can't take a derivative. I mean, I technically can, okay? But I want to have my derivative where I only have one single variable. And so what we're going to do is, since P equals this from our demand equation, I can always replace P with 70 minus 0.02Q because they are equivalent things. And so this will allow us to rewrite our revenue equation, our function, in terms of just one variable. I can use my distributive property and I get R equals 70Q minus 0.02Q squared. And now I can maximize this using my derivative, right? Let's take the derivative. That'll be a 70 minus 0.04Q. Set it equal to 0 to find your critical points. My critical points, I subtract 70 from both sides. Divide by negative 0.04. And I get Q equals 1750. Now, I need to make sure that this Q is a maximum. And so I'm going to draw my number line. All right, this is going to be R prime. We always like to label our number lines. And I'm going to put the value that makes my derivative 0 or my endpoint on there, right? I'm going to pick a number between 0 and 1750. I'm going to plug it into my derivative. My derivative is a pretty easy one to plug in. All right, I'm going to plug in a number between 0 and 1750, like 1. 70 minus 0.04 will be a positive. And then I'm going to pick a number that's greater than 1750, like a million. This term right here is going to be bigger. So 70 minus a bigger number would be a negative, right? And so that means that my regular revenue function is increasing on that interval and decreasing on that interval, which makes this a max. And also it makes this, since my derivative is positive right after 0, it makes this a minimum. So not only is this a local max, it's also a global max. Okay? And so since 17 represents a Q, and a Q represents the number of people who will attend, it says what attendance will maximize the revenue. In attendance of 1,750 people will maximize revenue. Part B, what price should be charged to maximize revenue? What price should be charged to maximize revenue? Well, if we know the quantity of people that should maximize revenue is 1,750, and we have our demand equation, all we have to do is substitute that 1,750 in for Q in our demand equation, and we get the price. So our price is going to be 70 minus 0.02 times 1,750, which I found, I think, to be 35. And since that is a price, my units here would be dollars. So the price that should be charged to maximize revenue is $35. So I know that the attendance to maximize revenue is Q equals 1,750 people. And I know the price P that we should charge to maximize revenue is $35. And so if I want to know the maximum actual revenue, well, again, we go back to our first statement, revenue is always price times quantity. I put that price in there, I multiply it by that quantity in there, I get 35 times 1,750, which is $61,250. And so this is the maximum revenue. All right, and this example includes the last example that we'll discuss in this video. We'll see you next time.